3.1 Graphs of polynomials. By definition, a polynomial with degree n looks something like this. F of x, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, many terms, plus a2 x squared plus a1x plus a0. So the degrees n should be greater or equal than 1. So that's the degree. And a0, a1, a2, a sub n are coefficients. They're real numbers, which we call coefficients. Okay, the domain of this polynomial, this function, is all real numbers, so there are no restrictions. Now let's look at some examples and determine if the following functions are polynomial. Determine if the following functions are polynomials. A, g of x equals 4 plus x to the third over x. So that denominator x is a problem and does not fit the description that we gave for the polynomial. All x is on the top, so this is not a polynomial. B, p of x equals 4x plus x to the third over x. Now we can quickly conclude here without simplifying. So let's try to simplify first. Divide by x all the terms on the top and simplify. So 4 plus x squared, which fits the description for a polynomial, and that is a polynomial. So just because you have x in the denominator, you cannot conclude that it's not a polynomial. If you try to expand, divide by x here, 4 over x plus x to the third over x. So that's 4 over x plus x squared. So this is the reason why it's not a polynomial. You have x in the denominator, which makes it rational. So C, q of x equals cube root of x. This is definitely not a polynomial. D, f of x equals absolute value of x. Again, it's not a polynomial. So again, we said n is the degree of the polynomial. That's the highest power of all the terms. And then the first term normally, the leading is called the leading term. A sub n x to the n, it's called the leading term. And a sub 0, the last term usually without x, is called constant term. So this is just a real number without x attached to it. So example, based on this knowledge, find the degree, the leading term, the leading coefficient, and constant term. So a polynomial f of x is 4x to the fifth minus 3x squared plus 2x minus 5. So let's start with the degree. The highest power is 5, so n equals 5. The leading term, it's not always the first term, but if it's in descending order, it is the first term. So this is the leading term, 4x to the fifth. The leading coefficient, that's the coefficient or the number in the leading term, that is 4. And the constant term is -5. It comes with the sign. Okay, so now we're going to talk about something called end behavior of polynomial functions. In other words, how does the graph behave on both ends, on the left or the right? So let's look at some examples that we are familiar with. So we know the graph of y equals x squared. It's the parabola. And regardless whether it's x squared or 2x squared, both ends will go up. So that's what's important. X to the fifth, this graph is a little bit flattened parabola, but both ends do go up as well. And then x to the sixth, we observe something similar. Both ends go up. So you notice the powers are odd numbers. So let's look at the powers being, the powers are even numbers and both ends go up. If the powers are odd, for example, y equals x to the third, we know the graph looks like this. So 1 n is down, 1 is up. So it's increasing. Y equals x to the fifth. We have a similar situation. So let's summarize this and say that for polynomials, if the degree n is even, we have the situation where both ends are up. And I have a little squiggly curve in the middle because we don't know how much it goes up or down. So in this case, the leading coefficient is positive. Both ends go up. And if the leading coefficient is negative, then both ends go down. And the second case, if the degree n is odd, then in the case of x to the third, we saw 1 n is up, 1 is down, but it starts from the bottom, goes up if the leading coefficient is positive, and then it falls down if the leading coefficient is negative. So it's best to have an example where we sketch the polynomial f of x equals -3, 2x minus 1, x plus 1 squared. So we'll talk about first end behavior. Before we graph it, we want to know how the graph behaves. To determine the end behavior, we need the degree. So what's n? If you follow mentally, you're going to have x squared times x, so it is 3. So it's odd. And what is the leading coefficient, which we call a sub n? So is it positive or negative? Because of this 3, it's -3, so it's negative. So we have a negative leading coefficient and odd degree. So the end behavior would look like this. It's falling down. Okay, the next thing we can consider is find the zeros and the multiplicity of each zero. So what are the zeros of our polynomial? You can easily find them if you set each factor equal to 0. So 2x minus 1 equals to 0 and x plus 1 equals to 0. Solve, you get x equals 1/2 and x equals -1. So that's how you find the zeros. You set the equation equal to 0. So 1/2 and -1. Now the multiplicity of each zero, it's how many times we have that 0. So the first one is just 1, but the second 0, you notice squared, which means the multiplicity is 2. So even multiplicity means when you graph, at that point, the graph will bounce off the x-axis. It's not going to cross it. So let's see, we have x and y, and we have the zeros, 1/2. So let's say this is 1/2, and we have -1, and we have the end behavior. So because -1 is even 0, that means when the graph comes above, it's going to bounce off, not going to cross, and then it's going to go down. So notice the end behavior now matches what we have written down. You can always make a table for more points in your graph to make it more accurate. So we can say x equals 0, which is easy to calculate, and we get 2.5. So that is our y-intercept right here, 2.5. And this concludes the section 3.1.